Hi everyone, welcome back to my YouTube channel. In this video, I will be explaining cache techniques, what they are, why they matter, and how they work to make computers faster. So, let's begin by understanding where cache fits in the memory hierarchy. So, faster memory, like the register and cache memory, are the closest to the CPU. They are very fast since they are very close to the CPU, yet they are small and they are very expensive. Looking at other memories like the main memory and the SSD, they are farther away from the CPU. They are very slow, yet very large, hence are used for bulk storage, and they are very cheap. So let's move on to the next slide. So some may ask, why cache memory? So the cache exists because the CPU works faster than the RAM, and this causes a bottleneck. And when we say a bottleneck, it's basically when it's a point where the system slows down, limiting overall performance. So the system slows down, limiting overall performance, and it really limits the performance or efficiency. And yeah, so that's how the CPU and the RAM works. Since the RAM is very slow and the CPU is fast, the CPU would constantly have to wait for the RAM. That's why we introduced cache. This cache here we are talking about is very fast. It's very fast and it stores data so that whenever the CPU needs data, it can come to the cache and will quickly get the data it needs. And also the cache stores data the CPU will likely reuse soon, so that it doesn't have to go to the RAM before it passes through all that process. So it becomes very efficient and fast. So let's move on to the next slide. So cache organization. In this one, cache is made up of lines. Each line stores a small block of memory. So a tag here is to identify it, and the bits here is to show whether the data is valid or modified. So to show that the data is modified, the valid bit does that job and the dirty bit modifies the data. Yeah, or change or indicates indicates rather, it indicates if the data is modified or changed. And this one checks for validity of the data. So yes, that those are the the cache lines here indicated. Let's move to the next slide. So here we are going to be looking at the cache mapping techniques. So in cache mapping techniques, we have three different types of mapping. First is the direct mapping. In this one, each memory block maps to one cache line. This is very simple, but then it causes conflict a lot. Yeah, it causes a lot of conflict. So we would like to avoid it in a way. And for the second one, which is the fully associative mapping, so this one can map to any cache line it wants, but yet it's flexible, but then very complex and slow. And for the last type is the set associative mapping. For that one, it can map to any it maps to all the set of lines. So here we have the 4-way is equal to 4 lines per set. So that one is it balances it perfectly, it gives it a balanced performance and so on. So that one is very effective. This one is very effective. um let's move on. So here is an example. Here we can see that the cache size being 4 megabytes, and here is the lines, which is the 16. So we can see that here the 4 megabytes direct mapped out, as we can see here, and a 32-bit address is split into the tag, the index, and the offset to find its data. And here we can see that to find the tag, we subtract the offset and the index, which is the 6 and the 16, from the address. So we can see 32 minus 6 plus 16 into brackets, which is the offset and the index, to get the 10 bits. This is a very nice example here. Hope you understand it. And let's move on to the next slide. So in this one, the cache reads and writes differently, as you can see here. The cache reads and also writes, but then it does it differently. So on a read hit, the data quickly returns, because as it gets the data, it returns back to the CPU, doesn't even wait, it's very fast. That's why we consider this cache. And for a read miss, the data is pulled from the RAM. So when the CPU goes to the cache, it doesn't find the data there. That means it has to be in the main memory, which is the RAM. So it goes there to pull it and store the data inside the cache. Yeah, and hence it's a mess, because like you have to get the data directly from the cache to the CPU. But in this case, it wasn't that. So that's how it works. And for the write operation, it can either be immediate or delayed. So for the write through here, you can see that it's as it writes to the cache, it also does to the main memory, so it's very immediate. But for the write back, it writes to the cache and wait for the main memory to update later. It uses the dirty bits, as we see here. So that one is delayed. So for the next is the cache performance. So for the cache performance here, we can see the formulas. So for the hit ratio is the percentage of hits. So like it's a percentage of success, something like that, because when the CPU goes to the cache and immediately gets the data, it's a hit. But when it doesn't, it's a miss. So this hit ratio is the percentage of hits, and we have effective access time here too, which is equal to hit ratio times cache access time, all into brackets, plus miss ratio times main memory access time. So we have an example here. They gave us the cache time to be 2 nanoseconds. This NS here stands for nanoseconds, because that's how we calculate for the time, dealt in nanoseconds. So, and for the RAM access time, or the main memory access time, it's 50 nanoseconds, and they give us the hit ratio to be 90%. So this is it. And for the hit ratio to be 90%, you know that the total percentage is 100%. So if the hit ratio is 90%, that means the remaining has to be 10%, which will be the miss ratio. That's what we have here. So the 90% was converted. That's how we have 0.9 here. And for the miss ratio, it was also converted from the 10% to this 0.1, as we see here, and times the cache time, which is 2 nanoseconds, and the RAM access time, which is the 50 nanoseconds here. So when we calculated, we got 6.8 nanoseconds. So that will be the effective access time we've gotten. Okay, so we've learned a lot actually today, and I hope you got everything that we learned today. Hope you grasped it. So to recap, cache reduces memory delays, as we've already learned. It uses efficient data storage strategies and significantly boosts system performance. So we would like cache very much. I think it's a very good thing. It's very good it was introduced into the computer, because it has made work very efficient and faster. Yes. So thank you very much for watching. I hope this gave you a clear picture of caching techniques in computer system. And if you found it helpful, please don't forget to like, comment, subscribe. Thank you very much. Bye.